That wasn't okay. So let's move on to the end of section 3. And I need to tell you about simply connected domains. These are very nice things. You'll learn about these in great detail if you do algebraic topology, which is a 4th-year subject. That's a very enjoyable one. A domain is simply connected if its boundary is connected. That's the definition I'm going to take more or less. If we want a more precise definition, take the algebraic topology course. Essentially, a domain is simply connected if it doesn't have any holes in it. Okay? So obviously, the first one doesn't have any holes in it, the second one has holes. The first one is not simply connected. So the first one is simply connected, the second one is not simply connected. Okay? You will need to be able to recognize simply connected domains. If I take an annulus, does anyone know what an annulus is? Yeah, I take a disk. By the way, a circle is the boundary of a disk. Disk is the whole thing. It's worth emphasizing. So an annulus is given by taking a disk and removing a concentric disk. So what does that mean? That means if I have something like this, I take the whole thing, and then I remove this. So this is a... Is this simply connected? No. Absolutely not. It has a hole in it. Okay, what about... Is this simply connected? If it's the region interior to it. If it's just the boundary, it's not
chicken foot, it's still simply connected.
Say again, sir?
Even though it looks like a chicken foot.
It looks like a chicken foot. Thank you.
I don't know, it's got the 3 kind of colors.
Is this, has everyone learned about convexity? Does everyone know what I mean by convex? No, okay. There's one shaking head. A set is convex if for any 2 points, the line which connects them is contained in them. So for instance, if I was to take a circle, I take 2 points, the line connecting them is always contained in it, right? No matter what 2 points I choose. So if I took this one, for instance, I take this point and this point, then it leaves it here. So this is not a convex set. Okay? Let me give you the following theorem, which I leave as a homework problem to prove. Convexity implies simply connected. It's convex. Any 2 points are contained in there. The line joining them is contained in there. Then it won't have any holes.
But the converse does not hold.
The converse is certainly not true by this chicken foot example. This is simply connected but not convex. Okay. Be aware of that because I may say, let omega be a convex set, is the following true? And you would need to know that convexity implies simply connectedness and then use whatever theorems I tell you about simply connectedness. Okay, here's an example of a vector field on a non-simply connected domain. Let's say that was not generated with MATLAB, that was generated with Mathematica. Okay, so let me ask some questions. Convexity is one of the other most important notions in mathematics. It's curious that natural selection has made us very good at recognizing convexity. There's no reason, I can't think of a reason why evolutionarily advantageous to...
Generally, convex things aren't pointy enough to stab you.
I can give you a convex thing that will stab you.
Take you how longer you got yourself in line.
Exactly.
The quickest path remains in the region.
Probably, maybe. Shortest distance, yeah, minima do exist in convex regions, but I don't know. Maybe 100 years ago it was just, you were more likely to get a mate if you could recognize convexity. I don't know if that's still the case. Yeah, it's strange. Anyway, that's something I think about. Okay, so let me just also mention that Euclidean space itself is simply connected. Euclidean space doesn't have any holes in it. What if I took this? Take R2 and I puncture it. It's called a punctured real or a punctured plane. Is that simply connected? Yes, no?
How about the line from the simply connected? What's
Simply connectedness. Let me give you.
the path from
Is that not convex? Not convex doesn't apply.
What about the line between?
Does it have a hole in it?
Yeah.
Where's the hole?
Zero.
There you go. It's not simply connected.
Very small hole.
Exactly.
In fact, it's an infinitesimally small hole.
When you use that expression, you assume that small makes sense. You're really assuming points have size when you use that. It's not clear that points have size. Okay, so I think I get you to do this on the assignment, but I will tell you anyway. If I look at this vector field, what's this vector field? The spiral, right? The domain on which this thing is defined, is that simply, by domain I mean maximal domain, on which you can make sense of this, is that a simply connected region? Why not? Because it has the whole of the origin. It's R2 minus the origin. It's not simply connected. That's something to bear in mind. I want to do an assignment problem, but I left it as the assignment, so I can't do it. It's very elementary. What I do is I get you to compute line integrals related to simply connectedness. You'll have fun with it. Okay, so you can do it more generally, not just for domains in the plane. You can do it for things on that are in R3. So here's the sphere and the torus. This thing is called the torus. These are very important examples of what are called Riemann surfaces. But the point is that the sphere is simply connected. The surface of it, I should say, is simply connected. The torus isn't. The torus has a hole in it. Okay, so
But just to clarify, on a torus,
yes,
if you select a point on the surface of the torus, you can reach any other point on the torus using a line.
but it's certainly not convex. Now, the precise definition of simply connectedness, I can justify to you why it's not simple. The way to understand simply connectedness is that if I was to just take an elastic band and I was to put it on the surface of what I'm in,
Yeah.
then if it was simply connected, I could always shrink the elastic band to a point.
Yeah.
You notice that on the torus, I can't do that. On the sphere, I can. If I take a basketball, I put an elastic band on it, I can always contract. But if I do it on the torus, you're eating a donut and you've got nothing better to do. You put an elastic band on it, you try to shrink it, it gets stuck by the central hole, so it's not simple. when I ask you these questions, I'm really going to stick with domains in the flow. Yeah.
So with an example like the torus, say it was hollow and there was just a hole in the surface at any point around the rim, would that mean it's not simply connected?
If I was to take so the torus is already not simply connected. You put another hole in it.
Well, yeah, okay, so maybe like a hollow sphere then.
You put a hole in the sphere, it will, let me try to say this without confusing you even more. If you puncture it, then it will undo and it will become something again. But I don't want to explain that any further. That's really the subject for algebraic topology. But for the most part, you'll only be dealing with domains in the class. Yeah.
With that definition of interconnected, as you go to higher dimensions, does the circle turn into a n-1 sphere?
Absolutely. The sphere, as long as you, so the circle isn't simply connected, the circle has a hole in it. Right? But S2, S3, and up to S a billion, and S infinity, 100% simply connected.
Sorry, I mean like the rubber band.
The rubber bands.
You replace the rubber band and you're like,
No, simply connectedness is always by taking a circle, in other words, an elastic band, onto your surface. If you want to take a sphere onto your surface, that's called two-connectedness, and these lead to what are called high homotopy groups. Okay? That's not the subject of this course. But it is one of the biggest unsolved problems is to understand the homotopy groups of spheres. So I'll leave that as a homework. So let me know if you figure it out.
Is there a Millennium Prize waiting for us?
No, but it is so hard that people believe that it can't be done. Like it's just a general belief that there are some homotopy groups of spheres that can just never be calculated. There have been a lot of homotopy groups of spheres that have been calculated, but there still are some that remain rather strange. The so-called exotic realities. Okay. So here I've got a vector field on R3. So if we're looking at the following theorem. But a smooth vector field on R3, vector fields are always smooth for our purposes. If it's so we saw that if it's a gradient field, it's what? Path independent. Here I'm saying the converse is true. If the vector field is defined on R3. Let me make an even stronger statement. So let's say, let me write this in a way that's convenient to understand. So, okay, take F to be a gradient field. So I'll make that this way, one box. Let's make path independence. Second box. Can anyone tell me a related notion to gradient fields? Someone who covered the while? Irritation. That's the other one I want to say. Let's say curl F 0. We call this rotational. And maybe the other one is, so by this I mean the line integral over a closed loop. Have I missed a notion? I don't think I've missed a notion relating to what we've spoken about.
Would you do the one where it's like if you
That's how you get the interventions. Yeah, no, that's good. So, okay, what do we know? What do we know? If this is true, is that true?
Yes.
Yes. certainly true. If this is true, is this true?
Yeah.
Yes. If this is true, is this true?
Yes.
Why is it true?
Because if you take the closed loop,
Yep.
it's exactly the same as the point going to itself.
Exactly. If I take a closed loop, I can cut it in half and realize it as two curves, opposite orientation, but equal because of path independence. Good. Okay. If this is true, is that true? That turns out to be true, but I haven't explained it. I'll let you guys figure that out. It's better if I just tell you all the implications and then we slowly flesh them out, at least from a pedagogical point of view. Okay. If this is true, is this true? There's a theorem on the board. Well, a theorem on the projector. It's on R3. It's not always true. So let me do it with a different color. And this means on simply connected domains. Obviously the theorem states it for R3, but that's just laziness. I could have done it more directly with simply, I could have done it more generally with simply connected domains. Okay. If this is true, is this true? Actually, let me say it again. If this is true, give me an example where this is true but this is not true. The spiral. The spiral example gives you an illustration of an irrotational vector field which is not a gradient field. So, let's see. Just to remind everyone. This is irrotational but not a gradient field.
I dislike the fact that it implies that spirals aren't curly.
It's irrotational. It is curvy. Sorry, I'm being silly. Sorry. No, you're right. Irrotational doesn't mean that's fine. Have a think. Any thinking I don't want to do is there's no curl. It's because, well, how would you, maybe we don't understand what curl means.
I don't know, it seems an interesting contradiction.
It's
to
because
me.
it's not spiraling in the plane.
Yeah.
It's spiraling over the plane. So that's really the key problem.
Yeah, still funny.
Still, yeah, that is humorous, yeah.
You can mathematically prove that spirals aren't curly.
Yeah, that is a unique fact. That's definitely one to take to a party. Okay, so this is not true, but what could be the source of the issue? Is there a question about that? The domain of this vector field is not simply connected. So, I'm going to make a claim without any justification that this is also true on simply connected domains.
Well, that means curl of 0 implies path independent.
Good observation about transitivity of implications. So, if I'm on a simply connected domain, or a convex domain, and I'm irrotational, then I'm a gradient field, then I'm path independent, then any integral over a line integral over a closed curve will vanish.
That implies curl implies
So you can just follow this flow chart as much as you want.
zero loopy thing.
That's right.
Zero curly thing.
That's right.
If
If simply connected. Yeah. Any string of these arrows, follow it to your heart's content. Yeah, it is. The vanishing of the curl of a magnetic field or something nonsense like that. Yeah. It's in Maxwell's equation. Is that right? Yeah, there it is. Okay. You know, if you so when I did make the mistake of checking water, I did ask why are we doing this complicated stuff, right? And so I intentionally didn't answer because I wanted to talk about it here. The first reason to do things in terms of differential forms, even though differential forms are more complicated, is firstly that the payoff will come when we do the integration. Okay, when we start doing Stokes' theorem, the divergence theorem, and so on, life is effortless. It will be effortless for you guys, but for instance, last year it would have been a nightmare. It is terribly confusing. When I took the course, I thought the subject had 15 theorems, but it was just one. The second is, if you wanted to do any kind of legitimate physics, you know, like general relativity, for instance, then you need to work in coordinate systems. You need to be able to change coordinate systems. If you do your standard curl and divergence, it assumes coordinates on R3, but if you're trying to do things for satellites and so on, you need coordinates on spheres and so on. So you want things that are independent of coordinates. My exterior derivative Hodge star gives you a coordinate independent formulation of Maxwell's equations. So that's the justification for why you should listen to what I say. The third one is you're assessed on it. So you learn it to your heart's content and to whatever extent you would like a good grade. Does anyone have any questions about these? This is something I will assess a lot. A common question would be, oh, actually, just wait for the assignment. Then you'll see. Okay, so I give a proof here, which is, it's actually quite elementary. It looks long, but it's long because I have to do a line integral over these things and then specify. But don't worry, you won't be asked to replicate the proof exam. Well, maybe not. Okay, so we saw that gradient fields are now, well, gradient fields are certainly irrotational and the converse is true. I don't even give a proof. This is curious. This is interesting. Let me talk about this for a moment. So, recall that I talked about solenoidal vector fields. Right? A solenoidal vector field is one that is given by the curl of something else. So, like for instance, if f is given by the curl of g, okay, then it would be solenoidal, right? And we saw that the divergence of such a thing was what? It was 0, because the divergence of the curl vanished. And why does the divergence of the curl vanish? Say again? Clairaut's theorem, and how do we summarize that in terms of
The fact that the two different orders of partial derivatives are equal.
That's the statement, right? What is the kind of, well, how do we prove it? Like when we wrote it down?
Well, the way that we proved it initially was just using the Hodge star operator.
And the exterior derivative.
The Hodge stars cancel and you end up with d squared, which equals 0.
Exactly. So let me just write it out for enjoyment. So we had star d star, that's the divergence. The curl was star d, and this would be omega g. Right? You guys are doing a lot of this in the workshop. Yep.
In the notes up there,
Yep.
theorem 3.6.17,
Hmm.
should that should say converse that if f is curl g, then if f is
Suppose the divergence vanishes, then f is the curl. This is a stronger statement. This is saying a converse to the thing we already know.
But then the remark right below it says that
The converse of the above theorem is not true. Okay, how? Yes, you're right, 100%. This is the one instance where the book is not perfect. This is exactly what I'm attempting to explain, and I will make a note of this. If you can you email me, and by you I mean only you and not everyone else, saying that remark 3.2.18 is incorrect. I would appreciate that. Yeah, so, okay, let me just finish this. So, the way we proved it was to do exactly this. We noted that star square was 1, so this gives me star d omega g, but since d square vanishes, this has to vanish. Okay, and the reason why it vanishes is use Claros. Okay. I may ask you to prove that. Okay. So just make sure you're aware of it.
Will that slightly shoddy proof be accepted?
Of course, this is not a shoddy proof, this is an excellent proof.
Good.
This is a yeah. I would put this in. I'll put it in a book. What's shoddy about this? I can't think of anything that.
No, you said Clairaut's theorem. I thought you might want to do it from original.
No, I've already proved Clairaut's theorem.
Huh?
I'm not going to prove, the axiom of real numbers every time I want to prove a statement about. I'm going to start on the ground. I don't. Okay, so about this. So it's natural to guess that we have this kind of what do I want to say? So you think of this as a derivative equals 0, and then this says it's the derivative of something else, and they're equivalent on simply connected domains. It's natural to think that, okay, if the divergence of a vector field vanishes, then it could be solenoid, if it's simply connected. So, we always know that the divergence of a solenoidal vector field is 0, but the converse, perhaps, given that the converse is always true on simply connected domains, you may think the converse is true on simply connected domains for this as well. That turns out to be false. The example I give here is an example of a vector field on, should be S2, I think. Should say S2. Which is, the sphere is certainly simply connected, but this gives you an example of a vector field which is divergence free. The word I use for that is incompressible, but it's not given by the curl of some other vector field. Yeah.
I think the remark is correct then, but the theorem is not. The theorem is not.
This is certainly, there's something incorrect here, which I will worry about later. But what's going on here is that the simply connectedness, that's measured by what's called the first de Rham cohomology group. But solenoidal vector fields, the ability to be written as a solenoidal vector field is measured by the second de Rham cohomology group. So the sphere has a vanishing first de Rham cohomology group, but its second de Rham cohomology group doesn't vanish, and so the implication is not true. That won't be assessed. Maybe. Depends if we get to chapter 5. If we get to chapter 5, then no. Okay. Does anyone have any questions before we?
That I found a mistake in the MATLAB code.
Say it again, sir?
That I think I found a mistake in the MATLAB code.
I don't want to hear about my librarians.
How about after
Those are the two worst words I think he's got. MATLAB was bad enough, but then
How about after the lecture, can I tell you about this?
if I'm in the mood. Of course. Okay. Which one of these, or which of these is simply connected?
Omega 1?
Is omega 1
Oh no, it's
simply
got
connected?
bits of things. No, of course not. It's got bits of
No.
layers.
That's-
Omega 4 is.
Does everyone agree that 4 is simply connected?
Yeah.
Is it convex?
Yeah.
Good. Okay, what about omega 3?
That's not simply connected.
Why not?
It's got big holes in
Everybody
it.
hold it. Omega 1 is not simply connected because it has holes in it. Those are lines. Is omega 2 simply connected?
Yeah. There's no hole.
No, there's no holes in it, that's fine. It's just confusing because the boundary is non-smooth.
Because if we can have a point which, if we can have a point removed from a thing, making it not simply connected, then surely if we have two simply connected spaces and they're only connected at one point, then that means they're simply connected.
100%. Is the intersection of simply connected domains simply connected? I have to think that up.
Yeah, it should be.
You sure?
No.
No, it's not.
No, it's good.
Take
Yeah, you could literally
take
take that
this.
one and inspect it with itself.
Yeah.
That's very much not simply connected.
Not even connected.
Mutually exclusive.
Yeah. I'm implicitly assuming that simply connected domains are connected. This is a union of simply connected domains.
Yes, but omega 2 isn't really
Omega 2 is not convex, that's correct. Omega 3 is certainly not convex, and omega 1 is certainly not convex. Is this simply connected? Probably fine.
But it's not, again, it's not.
Why is it not convex?
Because you can go through it from one.
That's right. Okay, I think I get you guys to do this one. Maybe I do, maybe I can't remember. Okay, yeah, I do put something like that on there, which is, that will check if you're paying attention. Okay? This is, yeah, well, you'll have fun with it. Okay, integration theory. Now we're getting to the, oh, we're on the last chapter already. Don't worry, this will be a bit long. This is actually my favorite quote, and actually one of my favorite mathematicians, Mr. Gromwell. He's the one who says kindergarten, is the one I stole from. He thinks analysis 3 is kindergarten. So he says that good mathematics is proving things that should be true, but great mathematics is proving things that shouldn't be true. The fundamental theorem of calculus is something that shouldn't be true. Okay, so we're now looking at higher integrals. We're going to look at surface integrals, which are, instead of integrating over curves, we're going to integrate over surfaces. Does that make sense? For that, you will require multiple integrals.
Fubini.
You need Fubini. I'm not going to teach you Fubini, but I'm going to assume you know it. We're going to, if you're not comfortable with it, you're going to get more uncomfortable because I'm not going to teach you. So if you're not comfortable with polar coordinates, spherical coordinates, cylindrical coordinates, things you should have done in first year, but I don't know what you were doing, make sure you know. And I put it in the book. So for instance, I talk about iterated integrals, and I even give an example of how to calculate it. I mentioned Fubini's theorem. Fubini says that under certain conditions, you can interchange the order. The integrals over general regions, make sure you know how to do that. Just show of hands, how many people are like, yeah, double integrals for a piece of paper, I do them every day. No, you tell me that often. Yes, how many people are like, okay, if I sit with it for an afternoon, I'll be okay.
Have more confidence
Yeah,
in yourselves.
yeah. Give me the class motivational.
I try my best.
We appreciate it. Okay, who is like, God help me, I can't even do C variable differential. I can't even spell integral. Anyone on that? Okay. We'll find out on the final exam. Get ahead of it now because integration is something that firstly, you've been doing it literally since kindergarten. You learned how to count in kindergarten, so integration is just counting, just a lot of it. It's supposed to be covered last year, so I expect you to be able to do it. Double integrals in polar coordinates especially. Okay? I like polar coordinates, so be prepared. This is polar coordinates, by the way. We've seen it before when we when we parameterize a circle. Here's something to bear in mind. I did this proof, the the other week, right? I computed the volume form. Let me say that if I use the expression area form or volume form, it means the top dimensional form on that space. So for instance, a volume form on R3 is just a 3 form. A volume form on R2 is a 2 form, and a volume form on the real line is a 1 form. Okay. Area form is just a volume form on R2. It's just a 2 form. Get used to it. Okay, so maybe let me check the answer so I know how to do it. Okay. Unlike half the cohort here, I do not spend every day doing double integrals. I do a lot of derivatives though, admittedly. I've spent 12 days calculating like 5 Leibniz rules, which is not something to be bragging about. Okay, let's have a look at this one. So I have an annulus. So an annulus is depicted above, and I want to compute the double integral over it of x squared plus y squared dA. Okay, so omega is the annulus. So we know this to be true. So you take a disk of radius 2 and cut out the disk of radius 1. So what I'm going to do when I notice that the region of integration is circular, so I can apply polar coordinates. Polar coordinates are r cos theta, r sine theta, and dx dy is r dr d theta. Yeah. I really encourage you to do that calculation again. I may assess something like that. That's something I would assess. Not that one specifically, but something like that. Maybe the spherical coordinate one that not even I can do. Okay, so what do we see? Well, I can write x squared plus y squared as r squared cos squared plus r squared sine squared, so it's just r squared. Omega is characterized by, well, the theta parameter is from 0 to 2 pi. The radial parameter is between 1 and 2. X squared plus y squared is r squared. And then I have r dr d theta. Yeah. Okay, there's no theta dependence, so I can just evaluate that. There's probably a few thinking in there. So I have 2 pi integral from 1 to 2 of r cubed dr. This one I know how to integrate r cubed, so I'll have 1/4 r to the 4, and between 1 and 2. Yeah, we know how to do that. It's pretty simple, right? Are you feeling on board? Yeah. Yeah. Okay, is that, yep.
So it might be a bit stupid, but the choice of the radial boundary, what was that for?
If you look at the annulus, the radius varies between 1 and 2. Now, is that what you asked?
So is it 4 on the right hand side of the boundary because that's r squared?
Yes. Yes. Everyone's with me? How many of you did polar coordinates, by the way?
Not me.
Like, read up high, because I need to complain with that department.
Wait, right.
We vaguely did it in.
Not vaguely, I mean, fully understood.
We were doing 10-14, but not 2.6.
Yeah, that's it.
Only right at the end isn't the last.
I'm honestly pissed off.
Then don't put it in the exam.
No, I'm putting it on the exam. I can guarantee that there will be some of these bloody polar coordinates.
Is the exam open book?
It's certainly not open book. Do I look like someone who gives you an open book exam? You just bring the textbook. Right? You don't want an open book exam, because an open book means I have to make questions really hard.
Yeah, that's true.
In fact, it's two-sided A4 sheet. Even that was generous. If I wasn't worried about people complaining, I would make it no-sided A4 sheet. Yeah.
But like
I know I'm probably being stupid here, but the area of that annulus, it's the difference of the area between a circle's radius 1 and a circle's radius 2.
That's right.
Well, the area
Pi
of,
r squared would be 4 pi minus 3 pi. Is that what that is?
I was just wondering why there was a to the power of 4 term in that, really.
Was it new or was it? It's a good question.
Yeah.
I'll leave it to you to tell me tomorrow morning. I don't know. I have to think about it for a moment. But it gives the right answer, correct? This will give me pi over 2, 2 to the 4, 16. Let's assume it gives the correct answer. This is certainly not correct.
I got 15 pi through as well.
So what is going on? Where have I gone?
Are we integrating this function x squared plus y
hang
squared?
on.
Oh yes, of course.
Well,
Sorry.
actually,
Sorry.
if you just integrate the a,
Yes, if you integrate 1, we get the error.
yeah.
We're not integrating 1, we're integrating x squared plus y. Yes, so. Yes. I get up at 3 a.m. before I come to this, by the way. That's why I could say things that are incorrect or have no idea to answer a basic question. So, it's better than one. Okay, so make sure you can do this. Okay, here's a cylindrical coordinates example. This one you should all go home and prove. Very elementary, it's almost immediate from the polar coordinates. Example. Okay, I'll give you another example that I'm nice. This is the character bill. This one it's quite so embarrassing. I filled up a page, it didn't give me what I wanted, so I gave up. But I encourage everyone to do that once in a while. I have done it correct once in my life. When I had my youth, I treasured it in. So that's a fun one. Okay. Yeah, so it's really question 1 that I wanted to put on the assignment. Okay, before we finish up, what did we do?
Line integrals.
Good, what else did we do?
Double.
Didn't really do it.
We started.
We started. What else did we do? We looked at, this is probably the most important thing that we did now. So we looked at gravitational vector fields, gradient fields, path independence, and then integral practice. Look at this, the exercises from 3.2. That probably has a lot of examples of things that I will put on the exam or on the assignment. Well, you'll get the assignment very, very soon. For instance, I give you a very complicated curve which you need to pay attention to. I have computer line integral. It's very intimidating. It's elementary if you know the theory. What did we start to look at? What was the fundamental theorem of calculus kind of discussion we had today?
Fundamental theorem of line integrals.
We looked at the fundamental theorem of line integrals, which is, everyone agrees, is just a formulation of the fundamental theorem of calculus. What did we start to say the fundamental theorem of calculus was?
Integration is due to the boundary, like to the derivative.
Yeah, so the opposite of a derivative is not an integral, it's the derivative of a function is like taking the boundary of a region of integration. Right? That's why we use the similar symbols, and the way to bridge them is to use the integral operator. Okay? If you want to read more about it, it's in chapter 5. If you don't, then I probably encourage you not to. Okay, if you want, have any questions? Just come to come. I'll see you guys tomorrow morning. What's that? Yes.
So the reason why this isn't three pies, we're not finding the area of an analyst, we're finding the integral of this function
Relatively short potential numbers.
Yes. This isn't a surface area. It's just double integral. Yeah, that's what.
Wasn't it supposed to equal the same as 4 pi minus pi?
No, because we're integrating a function over, it's not just the area. If it was just the area, it would be, 4 pi, or whatever it was. Yes.
So function over that.
When when I compute an integral over an interval, it's not the area of the interval, otherwise every integral from 0 to 1 would be 1.
Yeah.
That's exactly what happens.
Okay.
We're integrating the area of the function.
Yes.
So,
Yeah, okay. The alien was one that less than x.
yeah, it's the integral of this thing over this
Over
thing.
that region.
Yes.
So, just quickly, so